All right, today we're going to pull back the curtain and uncover the secret lives of the elements. We're splitting them into two giant and kind of rival families, the metals and the nonmetals. Let's get right into it. So, here's a question for you. What could a massive steel skyscraper possibly have in common with the invisible air you're breathing right now? I know, it sounds like a riddle, right? But trust me, by the end of this, you'll see how they're just two sides of the very same elemental coin.
You know, when you really get down to it, almost everything in our universe is built from one of two types of materials. So let's meet the two main characters in our story today, the metals and the nonmetals. Seriously, understanding these two is like having the cheat codes to understanding the world.
Okay, first up, let's talk about the metals. We see them everywhere. Our cars, our phones, the coins in our pockets. But what are the classic telltale signs that tell you an element has officially joined the metal club?
Well, metals have a very distinct personality. For starters, they're shiny. That's a property called luster. Just think of gold jewelry. They're also malleable, which is a fancy way of saying you can hammer them into really thin sheets like aluminum foil. Plus, they're ductile, so you can stretch them out into wires, like all the copper wiring in our walls. And oh yeah, they're sonorous. If you strike a metal, it makes that classic ringing sound, just like a bell. But maybe their biggest, most important superpower is conductivity. Metals are absolutely fantastic at letting heat and electricity flow through them. It's the whole reason your cooking pans are made of metal and our entire power grid relies on metal wires. This is a huge one, a really crucial point. Of course, just when you think you've got them all figured out, chemistry loves to throw a curveball. Take mercury. It's a metal, but it's a liquid at room temperature. What? And then you have sodium and potassium, which are so incredibly soft you can literally slice them with a knife. Even lead is kind of weird. For a metal, it's surprisingly dull and not very strong. See? These exceptions are what make chemistry so much fun. All right, it's time to meet the other side of the elemental family, the nonmetals. And you're going to see that in pretty much every single way, they are the polar opposite of the metals we just talked about. So if metals are shiny, nonmetals are usually dull, like a yellow chunk of sulfur. If metals are strong, a lot of nonmetals are brittle solids that would just shatter if you hit them. Or they're not even solid, they're gases. They are terrible conductors of heat and electricity. And if you tap a piece of coal, it just makes a dull thud. Definitely not sonorous.
And you better believe the nonmetals have their own superstar rule breakers too. Carbon is the biggest one. On one hand, it gives us graphite, the stuff in your pencil, which is a nonmetal that actually conducts electricity. And on the other hand, it gives us diamond, the hardest natural thing on the planet. Then there's bromine, another rare liquid element. Wild, right?
Okay, so we've got these two groups with totally opposite personalities. But why? What is the one tiny, fundamental secret that explains all of these massive differences? Well, the answer is smaller than an atom itself. That's it. That's the secret. All those properties we just went through, shiny or dull, strong or brittle, a good conductor or a bad one, it all boils down to one simple behavior: how they treat their electrons. So here it is, the core difference. Think of it like this. Metals are generous. They're givers. They are always looking to get rid of their outer electrons. Nonmetals, though, they're takers. They desperately want to grab more electrons. This one simple tendency, giving versus taking, explains everything. So when a metal atom does what it does best and gives away a negatively charged electron, it now has more positive protons than negative electrons. That imbalance gives it a positive charge, and we call that positive ion a cation. And on the flip side, when a nonmetal atom acts like a taker and grabs an extra electron, it gets an overall negative charge, and we call that negative ion an anion. This whole game of give and take is pretty much the basis for all of chemistry. Now, this constant dance of giving and taking electrons isn't just some weird atomic habit. No, it's exactly how elements react and bond together to form every single compound that makes up our entire world. Now, some metals are way more eager to give away their electrons than others. We can actually rank them in what's called a reactivity series. Think of it like a power ranking. At the very top, you have potassium, which is extremely reactive. And way down at the bottom, you have gold, which is super stable and unreactive. This list is awesome because it lets us predict how different metals are going to behave in chemical reactions. So what happens when a giver meets a taker? Well, you get what's called an ionic bond. A metal like sodium will literally hand over its electron to a nonmetal like chlorine. The sodium becomes a positive cation, the chlorine becomes a negative anion, and then that old rule, opposites attract, kicks in with a vengeance, forming a super strong bond. And just like that, you've made table salt. But what happens when two takers meet, two nonmetals that both desperately want more electrons? Well, neither one is strong enough to just rip an electron away from the other, so they have to compromise. They make a deal to share electrons, creating a stable connection called a covalent bond. It's a total team effort, and it's how molecules like water get made. Okay, let's zoom back out from the atomic level. We've seen how these tiny little electrons completely dictate how elements behave. Now, let's connect these chemical secrets back to the big, real world we see and touch every single day. So here's a quick summary, a little scorecard. Electrons, metals lose them, nonmetals gain them. Conductivity, metals are good, nonmetals are poor. Bonding, metals form ionic bonds with nonmetals, while nonmetals form covalent bonds with each other. It's a perfect snapshot of their completely opposite natures. And here's the cool thing, we don't always have to use metals in their pure form. We get creative. We mix them together to create alloys, which are basically super materials designed for a specific job. You mix iron with a little bit of carbon, and you get incredibly strong steel. You add some chromium and nickel to that, and boom, you get stainless steel that won't rust. It's us using chemistry to build better stuff. So why does any of this matter? Just look at the jobs they do in our world. Metals are our builders. Iron gives us our buildings and bridges, copper powers our electrical grid, and we use aluminum for all sorts of everyday things. But the nonmetals, they're what sustain us. We need oxygen to breathe, nitrogen for the fertilizers that grow our food, and chlorine to keep our water safe to drink. We absolutely need both. Which brings us all the way back to that first question. A skyscraper, built from metal, and the air we breathe filled with nonmetals. What do they have in common? They perfectly represent the two essential, opposing, but equally vital halves of our elemental world. And that's really the ultimate takeaway here. One group, the metals, builds the very structure of our civilization. The other group, the nonmetals, provides the very substance of life itself. Their opposite natures, all driven by the simple behavior of tiny electrons, work in this perfect, incredible balance to create everything around us. Thanks for tuning in.